Let me quickly summarize what all we have covered. We started out by saying we will cover the we will represent the conversion of a continuous time signal to a discrete time signal through a C to D converter. The time axis is discretized, but the amplitude still remains continuous. However, if you pass it through another stage, which is a quantizer, then you will get a signal that is discrete in time and discrete in amplitude. That becomes a digital signal. We said what is the definition of uniform sampling. If you have uniform sampling and quantization, you can represent a digital signal in terms of a number of bits, because number of samples per second into the number of bits per sample tells you what is the bit rate for the representation of the discrete time of the digital signal. A sequence represented by a string of numbers, but you must always identify what is the origin. That is important for us. Then we looked at the aspect of when Nyquist condition will be applied. It is applied in the context of a band limited signal. After that, we looked at the 4 basic types of continuous time signals: unit step, Dirac delta, exponential functions and sinusoidal functions. We looked at the corresponding discrete time counterparts of them. Unit sample, exactly like the Dirac delta, except that the amplitude of the unit sample is equal to 1. Unit step, like the continuous time unit step, starts at time n equal to 0, goes all the way to n equal to infinity. Exponential is of the form a alpha power n. Depending upon what value of alpha you have, we said that you can have a growing exponential or a decaying exponential. If alpha happens to be negative, then you can get an oscillating, you will get an oscillating function, either growing or decaying, depend on the value of n. Then comes the last case where you have the sinusoidal functions. The sinusoidal functions can also be captured by means of the rate at which they oscillate. And if you have an exponential weighting, then you can have a sinusoid that is exponentially growing or exponentially decaying. Those are the various forms of discrete time signals. Then we looked at the basic operation of shifting. Shifting means that you're removing your time axis, and here maybe we can even go ahead and say if n naught is greater than 0, then we call it a delay. Why? Because the signal moves to the right, signal occurs later in time. On the other hand, if n naught is less than 0, we call it an advance. Okay. So, basically when you say y of n is equal to n plus 1, that means you have advanced the signal by 1 unit of time, n minus 1 delayed by 1 unit of time. Okay. And we saw how you could delay the unit sample or you could advance the unit sample and the corresponding, and using that basic notation we can write the x of n in terms of shifted scaled unit sample functions. Okay, and we looked at an example of that. Then the important operation of time reversal. When you replace y of n, you replace x of n as x of minus n. It's as if you kept a mirror at time n equal to 0 and basically everything shifted on either side. So, whatever was to the right of the 0 went to the left and whatever was the left went to the right. So, this is the aspect of time reversal. We did an example of that. Then looked at basic operations that you can do. If 2 sequences are there, you can add them together, you can multiply them together sample by sample. You can also do scalar addition, you can do scalar multiplication. All of them have got useful applications for us. So, I requested you to take a look and try out these examples. We can discuss the answer in the next time. How do you define the length of a finite length sequence? Okay, what are the 2 limits, and then if you have n1 and n2 are the 2 limits, then you take is n2 minus n1 plus 1, and we looked at a couple of examples. And in this context, if one of the limits goes to 0, then we then say okay, it is a right sided sequence, and if it starts from n equal to 0, we call it as a causal sequence. Similarly, if the limit goes to minus infinity, we call it a left sided sequence, and if it is a sequence where it starts at time n equal to minus 1 and goes to minus infinity, then we call it an anti-causal signal. So, therefore, a causal signal, anti-causal signal. Now, what is the u of n plus 1? Okay, it is not a causal signal. not causal. It is not anti-causal either, right? Because it does not satisfy, it's not a left-sided sequence. So if you have sequences which are of this type, then you say these are non-causal sequences. Basically, you're not saying anything about the causality. All you're saying is it does not satisfy the property needed for causality or the anti-causality. It is somewhere in between. It's not, and it's not does not belong to one of the above two categories. Then we looked at what is the definition of left-sided, right-sided, causal, anti-causal, and given a sequence, you should be able to classify it correctly in that regard. Final part that we covered in today's lecture was about discrete time sinusoids. The basic definition is A sine omega naught n plus phi or A cosine omega naught n plus phi. And then we looked at a behavior which is very interesting, that discrete time sinusoids are periodic in frequency, unlike continuous time sinusoids. And at the same time, we see this increasing of frequency from 0 to pi and then decreasing to 2 pi, increasing, decreasing. So basically this is the periodic behavior that we are seeing. Now in addition to that, not every discrete time sinusoid is periodic in time. So if you look at the definition, it requires the frequency 2 pi by omega naught to be a rational function. And if you do not satisfy the rational condition, then the discrete time sinusoid is not periodic. So for example, we saw that cosine 0.785 n was not a periodic function. On the other hand, cosine pi by 4 n, which is very close in value in terms of radian frequency, is actually periodic. So again, this is what we want to leave you with. So finally, for the Fourier series representation, you're looking at a time domain signal with period equal to n. How many sinusoids do we have with period equal to n? Only n sinusoids which are distinct, that have period equal to n, and therefore a Fourier series representation of a periodic signal in time will have n Fourier series coefficients, and therefore we now have an interest to move from the time domain into the Fourier domain to see what new insights we can gain about the discrete time signals. So with that, we will stop this session and pick it up from here in the next class. And again, I would definitely encourage you to do the reading from Oppenheim and Schaefer. We have basically covered sections 2.0, 2.1, 2.2 and 2.3. You can cover these portions, and then we will pick it up from there and build on that in the next class. Thank you.